this is our continuation of our section on projectile motion, and in here what we're going to look at is we're going to continue to look at projectile motion, but this time we're going to start off with an initially angled velocity. We're not going to roll it off the edge of tables anymore, where it only has horizontal component to start with. It'll have both horizontal and vertical. So in this case right here, we have a shell. A shell is fired at an angle of 30 degrees above a level plane with a speed of 120 meters per second. The question is, what is the maximum height of the shell? And so if we think about sort of what's going on here, basically what we have is we have a level plane. We have a shell which is fired at 30 degrees. So we have 30 degrees right in there. It should be a 30. It's going to travel a path until it hits the ground right down here. It should be parabolic, the parabola here. Its original speed is 120 meters per second. And the question is, what's the maximum height? Maximum height is basically going to be the spot that's right up here. And so for this, let's sort of take a look at what we've got here. Based on this, we would say that this distance right here, that's going to be our y distance right here. This from here back to where we started would be our x distance. And so we'll sort of keep those in mind as we work through this here. So let's set up our table on this. And so same type of thing. We're going to say x, we're going to say y. In this case right here, so the acceleration in x is going to be 0. There's nothing that's accelerating this. Once it's entered the air, once it's in free fall, once it's been fired, it has no acceleration in the x direction, as long as we ignore air resistance, of course. Our next one would be for y. This is on Earth. We'll assume that unless you're told otherwise. So negative 9.8. Let's look at our next one. Would be v naught x and v naught y, like this. So previously we just looked at the problem to find v naught x, but in this case right here, the speed 120 meters per second is not traveling in the x direction as it was in our previous examples. In this case, it's angled. And since it's angled, that means we are going to have to take that 120 and we are going to have to break it into two components, into an x component and into a y component. And so in order to do that, then we'd basically say, all right, let's take a look here. If this right here is 120, I have x, I have y, I know this is 30 degrees right in here, and so my x component right here, that's my vx, v naught x really, v naught x, is basically going to be equal to, well, it's going to be v times, in this case it's adjacent over hypotenuse, cosine, that's cosine 30, so it'll be 120 cosine of 30. And so if you do that math right there, that Vx cosine 30, I get 103.92. And so that means that our V naught x is 103? Just forgot what I just said here. 103.92. 0.92. So 103.92 for that. My y, on the other hand, would be 120 times the sine of 30. Because it's opposite over hypotenuse, that's sine, 120 over sine of 30. Sine of 30 is 1/2, so that makes that quite easy. And so 1/2 times 120 is just going to be 60 right there. And so note, we still use our trig to figure that out. And so that means that we know v naught y is going to be 60 meters per second. We've got that down quite nicely. And so that's basically for the most part, that's really the only difference you do as far as initial angled projectile motion versus horizontal direction. Is you simply have to find the x and y components at the beginning. And you do that by setting up your right triangle. You know what the hypotenuse is, and just solve for what the sides are. Just using trig. That's basically the only difference here between what we had the previous one and this one here. Vfx, since there's no acceleration, is also going to be 103.92. Probably ought to be green, but so Vfy, we do not know. At least not yet. We'll talk about, actually there is a way to figure it out, which we'll discuss in just a second here. Let's look at our dx and our dy. In this case right here, do we know the final x distance? Nothing tells us about that. Do we know the final y distance? Nothing tells us about that either. We don't know either one. And then we have time, which we also don't know. Now, I mentioned about that VFY. There is a way to figure it out because I want you to think about something. If I were to fire a shell into the air, if I were to throw any, or even throw something into the air, that the maximum height, if we think about what the y velocity is, the y velocity decreases, starts off high, it decreases as you go up, and then it increases in a negative direction once you start going down. at the very highest point, the y velocity is 0. And since we're looking for the maximum height, we're looking for the point where the y velocity is 0. And so we can say the final y velocity is 0 here. Once we've got that, that tells you a little bit of what we're going to do next here, because if we want to find the time, which is our key piece here, we know the acceleration in y, we know the original velocity in y, we know the final velocity in y, and so let's just go ahead and look at our acceleration equation. Acceleration is final velocity minus original velocity over time. So the acceleration, negative 9.8, equals the final velocity, which is 0, minus the original velocity, which is 60, over the time. And so we solve for t here, and so that ends up being negative 60 divided by negative 9.8, and so I get 6.122 if I'm doing my math right. So 6.122 seconds to get up to the halfway point. So 6.122, 6.122 like this. And we're looking for maximum height, so we want to find what this distance is here in the y direction, and so that means we're going to use our y distance equation, that distance dy is equal to 1/2 times the acceleration, which is negative 9.8, and so that basically is going to be negative 4.9. We've said that before, negative 4.9 t squared, but t, I just forgot things again. T, we already figured out, is 6.122. Squared, plus the original velocity, which is 60, positive 60, and watch out for signs. They do make a difference here, as they always do, 6.122. So negative 1/2, or 1/2 times acceleration times t squared plus the original velocity times time. So we got here, if we solve then for dy, that we end up getting 183.673. which would go to two significant figures here, so it'll just be 180 meters. And so this object, this shell, will reach a maximum height of 180 meters above the ground. And that's sort of where we start this off. So let's move on. Let's add a little more complexity to the system. And so if we do that, we say a shell is fired at an angle of 30 degrees, same as before, from atop a 250-meter tower above a level plane with a speed of 120 meters per second. And that's the shell's moving 120 meters per second, obviously not the plane. And so this is very similar to the previous problem. The only difference is our object is up in the air to start with. And so if this is our plane right here, instead of being from the ground, we now have some sort of tower that's going on right here. And from that tower, we're then firing this thing upward still at 120 meters per second. Those conditions haven't changed, but it's now going to go. We would expect that it's probably going to have a little longer range now because it starts off from a higher height as we sort of start this off here. So this is sort of what we've got going on here. So let's set up our table, same way we did before, of x and y. And so acceleration in x is going to be 0. Acceleration in y is going to be negative 9.8, same as before. Let's see, original velocity of x, well, that's one that's sort of similar to what we did last time, is that we know this 120 is breaking into two components. We have an x component, we have a y component. We know the angle inside that is going to be 30 degrees. And, well, have we changed our initial conditions? Not from last time. The same math we did before, where to find the y, we said y is the opposite angle, or the opposite side. So you want to use sine, so it would be 120 times sine of 30. And so the same way we figured out that 120 sine of 30 was going to be 60 right there. We know that for y, we're going to be 60 to start with. Same as it was last time. We do it the same way. We use the trig to figure out what that is. And for x, it would be 120 cosine of 30 for that interior angle right there, and that ends up being the 103.92. Do remember, in these cases, you have to go ahead and break those into components. You have to say that 120, since it's angled, break it into x components, y components, and those are your original velocities that we have here. So let's look at the next piece here. Vfx. Well, once again, no acceleration, so 103.42 doesn't change. Vfy, though, we are not looking for the high point here. It says, what is the range of the shell? Okay, the term range basically means the x distance from where it starts to where it ends. That's our dx right there. That is range. So range is dx. So height would be dy, range is dx. That's just sort of a definitional term that's sort of used right there. So we're looking for that right here. We're looking to find the point wherever this shell is right here. That's what we're trying to find. And so our VFY would be whatever speed it has at that point, which we don't know. We said before that if an object starts and ends at the same level, that we could use a little trick where that we know that whatever the original velocity in y is to be the same in the negative direction, but that's only true if they started at the same level. In this case, they don't. It ends up being, in this case, a good, 250 meters? Yeah, 250 meters below. That tower is 250 meters high. And so there's a difference in the height. We can't make that assumption, so we do not know what VFY is. It's an unknown for right now. Let's look at our next one here. Our next one will be our distances. Our distance x. Do we know what that is? Well, if we did, we'd be done. That's our range. That's what we're looking for. Our next one for the other one would be dy, which we know in this case it goes from 250 meters high down to the bottom here. And so it's going to drop by 250 meters. So we do know what dy is. It's negative 250 because it does drop by that distance. And our last one here would be the time, which we also do not know. So looking at these two, we want to find range, and so what we're looking for here is dx. That's what we want to know, but to find dx, we have to know what the time is. We don't know the time, so we'll have to use y to find our time. Looking at y, we know acceleration, we know original velocity, we know distance. That means we're going to want to use our distance formula. So we say negative 250 is equal to, that's our distance, is equal to 1/2 at squared, so negative 1/2, so 9.8 times 1/2. Negative 4.9 t squared plus the original velocity, which is 60 times t, and now we have to solve this for t. You say, ooh, that's a quadratic equation here, and no easy solution outside of just basically using quadratic formula. So negative b plus or minus the square root of 2ac over 2a. You can use that. If you do have other sets of equation solvers for solving that, you're free to use those as well. They do save a lot of time. We're just going to go ahead and just show you what that's going to end up being. If you were to solve this for t, if you go ahead and plug those through, let's see, you would end up getting, and I wrote this down earlier just to make sure I didn't mess up this. There are two roots for this one, 15.5301. And also negative 3.29 actually, 3.29. Once again, since this is quadratic formula, we do get two solutions here, but there's only one physical solution. It's obviously the case that this object did not hit the ground before it was fired, and so we can get rid of this negative solution here. That's the non-physical solution, and we're going to stick with the 15.5301 right there. That's going to be the value we're going to use here. So 15.5301, 15.5301. Now that we've got that, we now know the velocity, which does not change for x. We know the time. We can find the distance in x. And so the range, dx, over the time is equal to our velocity. That's sort of our definition of a constant velocity here. And so Vx is 103.92 is equal to dx, the range, over the time, 15.5, I did it again, 5301. And so when we solve that, we end up getting that the x distance dx is 1,613.94 meters. Two significant figures here, 250, it's 2, 120, that's 2. And so we're going to put 1,600 meters is the range. So this shell would travel 1,600 meters before hitting the ground if fired from this 250 meter high tower. So this is how we figure out range here. That's how that would work whenever you have a different heights on things. So let's go ahead and move on. So in this case right here, a shell is fired at an angle of 30 degrees from atop a 250 meter tower, same as before, above a level plane. How fast must the shell be fired to travel 2,000 meters? Well, we found last time that if we fired at 120 meters at 30 degrees from a 250 meter high tower, it only went about 1,600 meters. We need to get to 2,000. It's going to have to go faster, but we don't know how much faster. So that's what we have to figure out. So let's go ahead and let's try setting this up. The same basic conditions as last time as far as our tower and such. We have x, we have y, and so let's see what we know. AX, still 0. AY, still negative 9.8. For V naught X, do we know the original speed? No, it asks how fast. We'd have to know the original speed to figure out the X component of that speed. Well, that's what we're doing here, so we don't know V naught X. V naught Y, same problem. We'd have to know this how fast in order to break it into components to figure it out. We know the angle between them, but we don't really know what the magnitude is of that vector. And so we can't break it into components. So we don't know those two things. Let's look at our next one. VFX. Do we know the final speed of this when it hits the ground? No, we don't. Doesn't tell us any information about that either. What about VFY? Still nope. Nothing there either. So we're sort of 2 for 6 so far. Let's look at our next one here. Distance in X. We do know that one. We want to travel 2,000 meters, and so we know that's going to be 2,000 right there. DY. Yep, we know that one too because it started off at the top of a 250-meter tower, ended up at the ground. That's a distance change of negative 250. That is a 2 right there, so negative 250 meters right here. And our last ones would be the time, which we also don't know. Looking at this, you could say we're missing a whole lot more stuff than we have before. And that is sort of the reason why this problem is here. Looking at this, we really don't have any equation we can solve. Because here's what we could do here. We could look at, for example, at the X equation. Because, you know, if we want to find V naught X, we know V naught X and VFX are going to be the same thing. So let's just call both of these just Vx for right now. We know that Vx is going to be equal to the distance over the time in X. And the distance is 2,000 over the time is T. So we've got that. We can't solve it, but we've got it written out here. We know that for Y, that we can basically say for Y that we also know that the distance it travels, which is negative 250, is equal to 1/2 acceleration, so negative 4.9, times t squared plus v naught, which we don't know, v naught y, that's a y, times t, which we also don't know. Can't solve that either. Well, we have two equations, but let's look at the variables here. In our first equation right over here, we have two variables. We have t and we have vx. In this one, we also have t, but we have vy. So we don't even have two equations and two variables. We have two equations and three variables. So unless we can find some way to mix these up and connect them, we really can't solve this equation. We have three variables. We need three equations. But remember at the very beginning, we said that whenever you have x and y, is that the x and y equations are independent except for two things. They're not independent for time. Their times are the same in both of them. And so that's why we have times in both of these that we could use to go back and forth between them. But the other thing that is true, they're not independent in, is that their components are related by trigonometry. And in this case right here, our angle is still 30 degrees for this. And so we still know this is 30 degrees. And so if we look at our original x component and our original y component, that our v naught y and our v naught x right here are related by that angle. That if we basically said that the tangent of 30 degrees is going to be equal to opposite, which is v naught y, over adjacent, which is v naught x, we now have three equations with three variables. We have vx and vx. We have t and t, vy, v naught y, and v naught y. Three equations, three variables. We're going to do some substitution here. And so let's go ahead and let's work on through this and see what this would look like. So we already know that vx, which is really v naught x, really. I mean, that's sort of what we said. We called it vx, but v naught x is equal to 2,000 over t. So let's look at our tangent. So we say that tangent of 30 is going to be equal to v naught y over v naught x. Let's just multiply. Let's just solve for v naught y. Multiply the v naught x up. So v naught x tangent. So really, we're sort of saying v naught x up here, v naught x up here. Those just cancel, right? So v naught x tangent 30 equals v naught y. And so v naught x, though, is equal to 2,000 over t. And so I can say 2,000 times tangent 30 over t is equal to v naught y. That's quite nice, because if I know that, I can take that and I can plug it in for this v naught y right here. And now I have negative 250 is equal to negative 4.9 t squared plus my v naught y, which is basically 2,000 times tangent of 30 over t times what? T. Those t's cancel. That's very nice. Now I just have negative 250 is equal to negative 4.9 t squared plus 2,000 tangent of 30. This only has one variable, just t. And so if we went through here and said, so we'd say negative 250 minus 2,000 tangent 30 and divide both of those by negative 4.9 and take the square root of that. Once again, save a little space here. When you do that, you end up finding that t is equal to 16.9314. So 16.93 is our time. Woot. 16.93. 16.93. We know the times now. That's in seconds, of course. So we know the time. The question was how fast must the shell be fired, though. And so to find how fast, we're going to need to know, basically that's going to be effectively what this velocity is right up there, that hypotenuse. Now, if we know either one of the two components, we can find that using trig again. But and how fast would be a speed, so we don't have to worry about direction here. So let's find one of our two. Probably the easiest one to find here is going to be v naught x, because it's just v naught x equals 2,000 over t. And so if I solve this in here, I would say v naught x is equal to 2,000 divided by the time, 16.93 seconds. And so that gives me a v naught x. If you work that out at 118.124. And since we know, then we set up our triangle right here. This is v. This is v naught x, which is 118.124. We know this angle right here is still 30 degrees from the problem. And so there's the rest of our triangle here. We have adjacent and hypotenuse. Adjacent and hypotenuse is basically going to be cosine. And so that I know that cosine of 30 degrees is equal to the adjacent over the hypotenuse. So 118.124 divided by v. Do v up, basically solve for v, and once again to save some space here, you solve for v, we end up here with 136.398 if you go ahead and just solve it for it. And so two significant figures would round 136 to 140, and so this shell must be fired at 140 meters per second to reach a distance of 2,000 meters. And that's a reasonable answer, because we found previously that firing the shell at 120 meters at the same angle, 120 meters per second at the same angle will go 1,600 meters. So 140 meters per second would be reasonable to go 2,000. And so that would be about as complex as these projectile motion problems get. If you get to a situation where you're stuck, where there's no way basically to figure out the information there, write out your equations and see if you do a substitution. At most, you'll have a situation like this, where you have three different equations and three different variables. And basically, well, whenever you get a situation like that, we have basically two equations and three variables, and two of which are components of each other, use the trig. Use the trig to solve them. And that's going to let you basically solve out the rest of this situation and solve for your answer.